Have you ever noticed that the Boeing 737 looks strange? Its engines seem to be flattened from below, and its wheels stick out even after takeoff. At first glance, it seems like an old design, a cost-saving measure, or simply an outdated aircraft. But here's the paradox. The 737 is the most widely produced jetliner in history. Over 12,000 aircraft, nearly 60 years of production, and it's still flying all over the world. So why has an airplane that looks so unusual turned out to be so successful? Today we'll explore why the Boeing 737 has flat engines and why its landing gear doesn't retract into the fuselage. And you'll see that behind these peculiarities lies not compromise, but brilliant engineering logic. The philosophy of the Boeing 737, an aircraft designed from the ground up. To understand the 737, we need to go back to the 1960s. Boeing didn't set out to build the world's most popular aircraft. They simply needed a simple regional airliner for short and medium-haul routes. It had to fly to small airports, operate where there were no jet bridges or complex equipment, and be serviced quickly and cheaply. At that time, luggage wasn't loaded into containers. It was simply thrown inside by hand. Refueling, passenger boarding, maintenance. Everything took place directly from the ground. So the engineers made a key decision that determined the aircraft's fate for the next decade. They made the BOE 737 as low as possible. A low fuselage, low wings, and minimal ground clearance. Passengers could board via a built-in staircase. Ground crew could work without lifts. And airports could handle the aircraft without major infrastructure. And at the time of its creation, it was the perfect solution. No one suspected back then that this very low profile would, a decade later, force engineers to change the shape of the engines, leave the wheels exposed, and literally squeeze every millimeter out of the design. But this is exactly where the entire history of the Boeing 737 begins. Why weren't there any problems at all before? The first Boeing 737 versions, the 100 and 200, were equipped with Pratt & Whitney JT8D turbojet engines. By today's standards, they were narrow, long, and relatively simple. In shape, they resembled a cigar. Small diameter, almost a perfect circle. All thrust was generated by the jet of hot gases passing through the engine. And here's the key point. Such engines didn't need a huge fan at the front, which meant they fit easily under the 737's low-swept wing. They had enough clearance. The risk of scraping the runway wasn't even considered. At that time, the 737's layout was ideal. The aircraft was low-slung, maintenance was convenient, the engine sat neatly under the wing, no compromises. But everything changed when the aviation industry began competing not for speed, but for fuel efficiency. In the late 1970s and early 1980s, the industry finally realized that the future lay with turbofan engines. Their operating principle differs from that of older jet engines. Inside, there is still a jet core, a compressor, a combustion chamber, and a turbine. But the main thrust is generated by a large fan at the engine's inlet. It draws in a massive volume of cold air, which flows around the engine's exterior. It is this accelerated airflow that provides most of the thrust, while the hot jet from the core merely supplements its work. The advantages are obvious: lower fuel consumption, quieter operation, and greater efficiency. The downside is also obvious. The engine's diameter increases dramatically, and this is where Boeing runs up against its own past. The 737 was already low-slung with short landing gear struts and minimal ground clearance. The new CFM56 engine simply wouldn't fit under the wing in its standard round shape. Boeing faced a choice: completely redesign the aircraft, new landing gear, new wing, new certification, or try to fit the new engine into the old design. As we now know, they chose the second path. And this is where the most interesting engineering solutions in the history of the 737 begin. And when you see a Boeing 737 engine, almost the same question always comes up. Why does it look strange? Why does it look like it's been flattened from below? It's important to understand one thing right away. The Boeing 737 engine is completely round on the inside. The fan is round, the compressor is round. The entire interior of the engine is round, just like in any other airliner. But the engine casing, or more precisely, the lower part of the air intake, does indeed look flattened. And this isn't a design choice or a whim of the engineers. It was a necessary solution to a dead end. First, the engine was moved slightly forward, in front of the wing. This helped improve the aircraft's balance and geometrically raise the engine above the ground. Second, the lower part of the nacelle was made flatter to gain a few more centimeters of clearance. Third, the layout of the engine components was changed. The drive housing and part of the auxiliary systems were placed on the sides of the nacelle, freeing up the lower part of the engine. This is precisely why the 737 developed its characteristic engine shape with cheeks, making it easily recognizable. Why was all this necessary? First, ground clearance, the distance between the engine and the ground. Second, safety, especially during crosswind landings when the aircraft may bank slightly. And third, to avoid having to redesign the landing gear or rebuild the aircraft from scratch. And here's the key point. It's an ugly solution. It's an engineering compromise. Just make it fly, and it worked. If the aircraft is so low that the engine shape had to be changed for this reason, a logical question arises. Where did the landing gear doors go? Why, on a Boeing 737, do the wheels remain outside even when the landing gear is retracted, as if the aircraft forgot to close something? It actually didn't forget. This is also part of the same philosophy. At first glance, it looks like a relic of the past, as if the plane was designed in a hurry or they cut corners somewhere. The reason here is very simple and very strict. There simply isn't room to fully retract the wheels. The Boeing 737 was originally designed to be as low to the ground as possible. This was done for operation at regional airports of the 1960s, without jet bridges, without container loading, and without complex ground equipment. When the main landing gear legs retract, they fit into an extremely compact bay. This bay, which is low in height, is tightly packed with systems and simply isn't designed to accommodate additional mechanisms. To fully enclose the wheels, Boeing would have had to increase the bay's volume, redesign the wing's structural elements, add a complex system of flaps, increase the aircraft's weight, and undergo full recertification. And then a key engineering question arose. Is it even necessary to enclose the wheels at all? Full-fledged landing gear doors are not just doors. They involve additional hydraulic actuators, position sensors, locks, control logic, and dozens of potential failure points. Each of these elements adds weight, complicates maintenance, and increases the likelihood of flight delays. Boeing approached the task pragmatically. There is an aerodynamic benefit to covering the wheels, but it is not critical for an aircraft of this class. And so a decision was made that fits perfectly with the character of the 737. Remove everything unnecessary and keep only what is truly needed. They didn't fully enclose the wheels. They only covered the wing, fuselage, and critical areas, compensating for the rest in other ways. The 737's main wheels are fitted with special smooth wheel covers. They aren't just for looks. When the landing gear is retracted, the outer surface of the wheel, together with the cover, forms a relatively streamlined surface. This drastically reduces drag to such an extent that if a cover is damaged or lost, airlines are required to account for a fuel penalty when planning a flight. In other words, it is not a decorative detail, but a real aerodynamic element. The next engineering challenge is protecting the landing gear bay from dirt, debris, and foreign objects. The main landing gear bay of the 737 is not an empty compartment. Inside it are hydraulic system components, high-pressure lines, cables, and control mechanisms, and in some configurations, engine fire suppression system cylinders. Since the wheels remain exposed when retracted, there was a risk of foreign objects entering the bay. On early 737 models, Boeing attempted to solve this problem using inflatable seals, which inflated after the landing gear was retracted and sealed the gap. However, in practice, this solution proved unsuccessful. The seals lost their air tightness, were susceptible to wear and damage, frequently triggered cabin leak warnings, and led to delays in additional maintenance. As a result, Boeing engineers abandoned the complex system and switched to a more reliable solution, a multi-layer rubber seal without moving parts. These seals do not use pressure, do not require hydraulics, and have no actuators. yet they form a robust physical barrier between the landing gear bay and the outside environment. Minimal mechanisms, minimal failures, maximum reliability. Boeing engineers took into account one of the most dangerous scenarios, a tire blowout. If a damaged wheel begins to retract into the bay, cord fragments and metal parts could damage hydraulic lines and other critical systems located nearby. To prevent this, on the Boeing 737, the wheels are automatically braked when the landing gear is retracted, sharply reducing their rotational speed. Additionally, the system includes hydraulic safety valves. If something goes wrong and pressure in the system drops, the landing gear simply does not retract fully and remains extended. This is a deliberate engineering choice. It is better to fly with the landing gear extended than to hide the problem inside the aircraft and damage critical systems. Why has this solution been in use for over half a century? The most compelling argument in favor of this entire design is time. The Boeing 737 has been flying for over 50 years. During this time, aviation has changed radically. New materials, digital cockpits, and completely different engines have emerged. Requirements for noise, environmental impact, and safety have become stricter. Airplanes that were considered modern just 20 to 30 years ago have long since become history, but the Boeing 737 remains. It has survived several generations of engines. The transition from turbojet to turbofan, stricter noise and emissions regulations, new certification standards, and fierce competition from Airbus and other manufacturers. And through it all, the exposed wheels have remained exposed. The simple and reliable landing gear design has remained. The philosophy of minimalism and the rejection of unnecessary mechanisms has remained. Even the 737 MAX, the most modern and most talked about member of the family, has retained this concept because, from an engineering standpoint, it still works. Reliably, predictably, and proven by millions of takeoff and landing cycles. And here's the key point. In aviation, there is no tradition for tradition's sake. If a decision is truly bad, unsafe, or too inefficient, it doesn't last for decades. It gets changed, removed, or banned. Mistakes in aviation don't survive half a century of service. The Boeing 737 isn't a perfect aircraft. It isn't the most beautiful, the most technologically advanced, or the cleanest from an engineering standpoint, but it is incredibly resilient, surprisingly flexible, and utterly honest in its logic. This is an aircraft in which many design choices were not conceived in comfortable conditions from a blank slate, but as responses to real-world constraints. Altitude, an aging airframe, airline requirements, and time pressures. That is precisely why it turned out the way it did. And perhaps the main question here is no longer for BOE's engineers, but for you and me. Would you choose the ideal aircraft designed from scratch or the one that has been proving time and again for 60 years straight that it works? Let us know in the comments. I'd be very interested to read your thoughts.